Hello everyone, this video is going to be a quick introduction to NVIDIA CUDA, which is NVIDIA's code platform that lets you write programs for their graphics cards. I'm going to cover some background information about the origins of CUDA, and then I'll cover some important theory about GPU programming in general. Finally, I'll give a code example to help you get started and visualize how a real CUDA program works. So before we start writing CUDA programs, it's important to learn about its origins, because GPUs have existed for a long time before things like CUDA. Originally, GPUs were only designed to do graphics computations. That's why they're named graphics processing units. What this means is that programmers would only be able to interact with GPUs through this graphics pipeline that you can see on the right. In other words, the primitives they worked with were pixels and vertices and textures, and the operations they had access to were only graphics related, rather than having a very general purpose programming language like we have today. It took many years for people to have a demand for general purpose computation on GPUs. But in the early 2000s, researchers at universities started realizing that these GPUs would be really good at general purpose parallel computation, if only there was a way to actually program them in that fashion. In this research paper on the right from 2002, we can see that Thompson et al. Demonstrated one such way to jerry-rig a method for general purpose computation on top of the graphics pipeline, but this was just one of many very hacky solutions. By 2007, NVIDIA realized that there was a demand for general-purpose GPU, and they released the CUDA platform, which provided these general-purpose interfaces to their hardware in a much more streamlined package. This was a genius move on their part, and the early adoption of GPGPU is part of the reason that they currently have dominance in the GPU market today. So now I want to compare general-purpose GPU programming with regular old-school multi-threaded CPU programming, in this case done with pthreads. First, I want to point out that when you work with pthreads, you have to manually create each thread separately and pass in a specific work function to each one. On the other hand, with CUDA, you have access to these kernel calls that you can see here, where you specify the function, which in this case is in the front and it's called kernel function, as well as the dimensions of the kernel with these two parameters blockdim and threaddim. But we'll cover more about this in the next slide. I just want to point out here that with CUDA, we spawn many threads all at once. Next, I want to point out that the thread functions that pthreads uses are just regular old functions, and there's nothing special about how they're compiled. In CUDA, though, only specific device functions that are compiled to run on the GPU can be kernel functions, and they also have access to some useful information within their function context. Another really important difference between CUDA and multi-threaded programming is that with pthreads, you have to keep track of all the threads yourself, whether that's through a thread pool or some other method. CUDA, on the other hand, is very structured, and using only those dimensions I mentioned earlier, it keeps track of all the threads for you. This, in combination with the next bullet point, is why GPUs can be so efficient. So GPUs use something called single instruction multiple data, or what NVIDIA calls it, which is single instruction multiple threads, in order to have many sibling threads, which are running the same function, use single processor instructions on multiple registers at the same time. So this is extremely fast, but it also means that your kernel functions must all be in sync, and they can't really branch significantly with things like if statements, as this would cause the threads to actually run sequentially since the SIMD strategy doesn't work anymore. So pthreads, on the other hand, can have very different functions in each thread, and there's no major repercussions to this. So this allows CPU threads to be split, for example, like with one thread listening to network traffic and another few threads just doing computations. So all this is to say that GPUs can be really fast in some situations, but you have to keep in mind that a lot of applications like web servers are much more well suited to be CPU programs. So now I'll cover the thread structure that I was talking about earlier, because it's really important to understand that when writing GPU programs. So a kernel is a device function that can be run by the GPU in parallel. Each thread, which is basically just an execution context, runs this kernel when we make a kernel call. From our perspective, they all happen at the same time. So threads, in turn, are organized together into blocks of threads. Blocks then are organized together into grids of blocks. And one small note here that within blocks, the threads are actually grouped up into groups of 32 threads, which we call warps. But this isn't really super important right now, and it has to do with the SIMD architecture I mentioned earlier. Also, this hierarchy is not just one-dimensional. So for example, the block we see here has 12 threads within it, but they're not just like 0 through 11. They actually have two coordinates, an x and a y, and they're arranged in a square shape. So you can also extend this to 3 dimensions, and this is also true for the blocks that are arranged within the grids. So the reason for the dimensionality is because for many GPU applications like matrix operations, it allows for greater efficiency, but there's really nothing stopping you from only using one dimension in your applications. The hierarchy of threads and blocks and grids is pertinent because it has to do with which threads can share device memory and how execution is grouped on the device, but we'll get into that in the next slides. So we know from CPU programs that we have heap and stack memory, but in GPU programs we have three main types of memory with different uses and speeds. So first we have the global device memory, which you can see here are the chips under the red lines. You can see that it's actually separated from the silicon, which makes it slower to access, although it's still much faster than accessing host memory on your RAM sticks. So the rest of the memory is actually on the silicon. So next we have local memory, which is the fastest, and it's unique to each thread, so each thread has their own local memory space. Finally, we have a really useful thing called shared memory, which is shared between all the threads in a block. So this is really useful for many applications where you want to build a data structure, but you want to avoid thrashing the global memory and slowing down the program. So for example, let's say all the threads in the block, they build part of an array within their shared memory. So once this is complete, we can just have one thread copy the entire shared memory block into the corresponding space in the global memory array. And that way we reduce the overall number of global memory writes, which we know are much slower than shared memory writes. So if you want to learn more about how to carefully structure memory accesses, you can look up coalesced memory access patterns and bank conflicts. Although they're really not necessary to start writing CUDA programs, they're just very important if you want to try to write very high performant code. Okay, so now let's look at some CUDA syntax and some useful functions before we start writing our first program. So CUDA is a C++ extension. So much of the syntax is shared. You have access to three new identifiers within the .cu and .cuh files, which are global, device, and host. So these go before functions, and they tell the CUDA compiler whether to compile the function to run on the GPU. In the case of like a kernel call, we use global, and device is used to mark functions that can be called from within kernel functions. So they're kind of like GPU functions. Host is the default, so it's not necessary, but it identifies functions that just are normally compiled for the CPU. You also have access to this 3 bracket notation within CUDA files, which is how we tell CUDA to launch our kernel. So in this code example, we have on top a kernel function getting defined that takes in a pointer to some memory on the GPU, but it doesn't do anything with it for this example. We also get our global thread index, which basically like taking our coordinates within the block and the block's coordinates within the grid and then linearizing them from 0 to n, where n is the total number of threads we have. This way we can tell each thread which spaces in memory to work on. Finally, we launch the kernel by writing the function name followed by 3 left brackets. Then inside of there we put the number of blocks and then the number of threads per block, and then we put the closing brackets. So then you finish the function call just like normal by putting the parameters within parentheses at the end. So remember though that pointers you pass into the kernel function must be pointers to device memory, which I'll show you how to get on the next slide. Also keep in mind that in this case num blocks and num threads per block can just be regular integers, but CUDA supports data structures called dim3, which is just a 3-dimensional number. So that would be how you can create 2 or 3-dimensional blocks and grids by making num blocks be a dim3 with 3 values set instead of just 1, for example. So finally, here are the 3 most important CUDA functions that we basically use all the time. So the first one is called idiomatic, which takes in a pointer to a pointer variable, and it sets that pointer variable to point to an address in the GPU's global memory space of the desired amount, which you pass in with size t size. After we have that pointer set to a device pointer, we can then use CUDA memcopy to copy bytes from the host's memory, that's just normal memory in your C++ program, over to global memory that you just allocated, or the other way around. So keep in mind that you have to set the CUDA memcopy kind value to the correct value depending on which direction you're moving data. Also, don't forget to free the memory after you allocate, just like normal. Here we are inside of our coding environment, and I've created a sample CUDA file called sample.cu. You can see at the top here that I'm including CUDA runtime among a few other things that are going to be useful for the program. And I've also defined a function called printInts, which takes an array of uint32s along with its size, and it simply prints it out to stdcout. So this will be useful, when we're testing our code. Additionally, I've defined our kernel function here, and it's very simple. It just prints. And so just as a reminder, this will be run once per thread. And global, of course, indicates that it can be run on the device. So here's our main function, and what we're doing here is calling the kernel with a dimension of 1 block and 1 thread per block. So we would expect this print to only show up once. So let's go ahead and see that in action. So we can compile with NVCC, which stands for NVIDIA CUDA compiler, and we type in the source file first. We do -o and the name of the output, and we can just ignore that because I defined the buffer size and didn't use it. But here I can simply type in .-sample, and what do we notice? So there's no print coming out. And the reason for this is that these kernel calls are actually asynchronous, meaning that this program launches the kernel and then it doesn't wait for it to complete. So what we need to do is called CUDA device synchronize. And this is basically saying, wait for the CUDA calls to complete at this line until they finish, and then continue. So now when we compile and run, we'll see that the hello world comes out. And now if we increase this to say 10, we should expect 10 of them to come out. And also a side note, this device synchronize function is optional if you have a CUDA mem copy after it, because function calls like that by default cause this action to occur as well. Simply because we don't have that, we need to manually add it. Okay, so now let's create a buffer in here. And by the way, the goal of this program is going to simply be to copy bytes from one buffer to another, but we're going to have the GPU do it. So obviously this isn't an interesting function, but it's very informative as to how the GPUs are working. All right, so we have our buffer here, and we fill it in with ints from 0 to buffer size -1. Now what we want to do is allocate some space on the graphics card and copy this onto the graphics card. So what we need to do is create a pointer, and this pointer currently is pointing really to nowhere. I mean, it's set to null, but it's not actually set yet. So what we need to do is call CUDA malloc and have CUDA malloc populate this pointer with an address to the graphics card memory. So now we have space on the graphics card that's equivalent to our buffer, but again, it's located on the device. So now what we can do is CUDA mem copy these bytes into the device input. All right, so here we're copying the destination being device input and the source being our source buffer, and we simply copy all these bytes over. And again, don't forget that we have to tell CUDA which direction we're copying, otherwise the pointers can get confused. And so in this case, we're saying we're moving from host memory here onto the device memory. So now we can CUDA malloc a similar buffer for the output. And so the graphics card will read from the input and then populate the output. So this is really common in the GPU workflow. And for us, obviously, it's pointless here, but just for example's sake, you can pretend like some computation is happening before we populate the output. And again, we have CUDA malloc a buffer of the same size. So now what we want to do is modify our kernel function to take in pointers to these device memory blocks. And once we've changed our function definition, we can pass them in. And now what we can do is populate the output with the input. But first we need to figure out what index we're in, because each kernel, in this case 10 of them, is getting launched, but they need to know which slot in the output and which slot from the input to read and write from. So what we can do is get our universal index, which in this case, because we're launching it in a one-dimensional fashion, is only going to involve x coordinates. So this is our global, thread index, and what it does is it uniquely identifies the thread amongst all the other ones from all the other blocks. And this is how we can tell which space in memory to edit. So the logic behind this is that in this case we only have one block, so actually this isn't necessary. But what it's saying is, let's say we're on the 5th block. Well, we want to get the full size, the full amount of threads within each block, which in this case is the number of blocks times the index of the block we're in. So this is like saying how many indices is there before us just from other blocks. And then we're just saying which position are we in this current block. And again, recall that this can actually be an XYZ expression if you were to set this up with the dim3. But in our case, we're just going to stick with one-dimensional for now to keep it simple. So what we can do from here is say device output at I equals, idx. So what we've done here is we're taking our unique identifier and we're using that to tell us which slot in memory to access, in this case to read and to write. And so our kernel here, in this case 10, is exactly the right amount because our buffer size is 10. So what we should expect to see is that now the device output will be populated, but in a distributed fashion where each thread fills in its own slot. Of course, in order to get it out, we need to CUDA memcopy back to the host. So let's go ahead and create a destination buffer and then copy it back to the host. So now we've copied over, and again, recall we're going device to host this time, and we should in theory have filled in our destination buffer. So let's go ahead and set up a quick expression that just checks to make sure the destination matches the source. Okay, so what this function does is, this expression does is simply check the destination in the source and ensures that all the bytes are the same, in which case it prints out successful copy, otherwise it prints out unsuccessful copy. So let's go ahead and see how this works when we compile it and run it. So we can see that we get a successful copy. Now, let's say that our buffer size is bigger. For example, let's say that our buffer size is a very big number, like, well, in this case, we'll just set it to 50, for example. Now, in theory, we could increase this to 50, and that would work. But the thing is that the number of threads per block is limited, and modern graphics cards limited to about 1024, actually exactly 1024, and it used to be around 512. So common practice is to use numbers like 256, 512, or 1024. On the graphics card in this machine, I find that 512 is a bit more efficient, but it's very likely that 1024 works better in other graphics cards. But the key to note is that you can't always increase the number of threads, which means that occasionally you actually want each thread to fill in more than just one slot. So what we can do is pass in the total size in bytes to our kernel function. And let's say now that we've passed in the buffer size to our kernel function and we increase this buffer size to, let's say, 10,000. So this will be significantly bigger than the number of threads total, which again is 512 times 1. So for the sake of example, let's just set this to 2. It doesn't particularly matter, but in real life, you'll want this number to be like 512 or 1024, and this number could be in the range of a few hundred, for example. But in order to make our kernel work on arbitrary data sizes, we need to have a while expression in here. And so what we can say is while index is less than n, we perform the copy, but we also want to increment index such that the existing kernels we do have fully take care of the size, the input buffer, regardless of what size it is. So what we want to do here is add the full number of threads that we have to the index. So this way, let's say there's 10 total threads. Each 0 through 9 will fill in its corresponding spot, and then each one should in turn then solve the I plus total number of threads cell. So that way they don't step on each other's feet and we can still complete the total array. So the way we would get that would be blockdim.x times griddim.x. And the reason for this is because this again indicates the total number of threads within a block, and this indicates the total number of blocks within the grid. And so in theory, this is the total number of threads we have running at a time. So now that we've done this, again, note that our buffer size is significantly bigger than the total number of threads. We should hope for this to work correctly now. And we can see that the copy is successful. And so this has just been a basic example of an CUDA program. And you could imagine that in real life, these kernels are much more complicated than just copying one byte over. But the pattern of finding our global index like this, and then perhaps having a while loop so that regardless of the input size, our kernel function can handle it, that's a very common pattern within GPU programming. And now that you've learned CUDA malloc, CUDA memcopy, and of course we can't forget to CUDA free at the end as well, you have a very good understanding of like how CUDA programs look and how they operate. And from here, you can continue learning about the intricacies of memory management. And hopefully this video has been helpful to get you guys started with NVIDIA CUDA.